Hello everybody, it's me, just to say that I'm streaming every Tuesday, Thursday and Friday over on Twitch. So why not join in at twitch.tv/Toglajam. Minecraft's been around for 11 years, and from its alpha release to the latest 1.16 update, it's been used in classrooms to teach students about concepts ranging from electrical circuits to teaching coding through command blocks. But over the next couple of weeks, we're going to use it as a jumping off point to learn about some particle and astrophysics. Hello everybody, and welcome to the Science of, where today we're taking a look at the cubic world of Minecraft. Rather than do one big topic such as genetics or cell structure, we're going to be looking at some smaller concepts, but hopefully it'll all come together nicely. For the purpose of the next couple of videos, we'll be doing some mini science subs and delving into the fundamentals of physics, starting with particles and finishing up next week with the formation of planets and how gravity works. So you really can consider this first part as the science of science rather than the science of Minecraft. So let's start off by taking a look at the smallest part of physics and looking at some particles. So when you hear the term particle, you probably think back to your GCSE physics, where you learnt about the idea of everything being made up of atoms and subatomic particles, you know, protons, neutrons and electrons. The truth is, you can go even deeper into subatomic particles and find more than those you normally see in normal matter. These kind of particles are found in cosmic rays and particle accelerator studies, and these normally decay far too quickly to be studied properly. Now of course, this is a very large topic to cover, so let's start off by looking at the largest particles called hadrons. Hadrons are made up of smaller particles called quarks, and can be further split down into two more groups called baryons, which contain protons and neutrons, and mesons, which include particles called pions and kaons. These particles are incredibly unstable and are the lightest hadrons. The main difference between baryons and mesons is that baryons are made up of three quarks, whereas mesons are made up of a quark and an antiquark. There are 6 types of quark which exist: up, down, strange, charm, truth and beauty. These quarks have 3 properties which need to be conserved in any particle interaction: charge, baryon number and strangeness. And then of course for every quark you also have the antimatter equivalent, the antiquark. The most important thing about antiquarks and antimatter in general is that when an antiparticle meets its corresponding particle, they annihilate each other. During these interactions, the particles collide, and their mass is converted instantaneously into energy. So the next group of particles after hadrons are leptons. Leptons are fundamental particles which are not made up of quarks. These are much simpler than hadrons and include electrons, muons, tauons, and all of these have a negative charge. As well as the regular lepton particles, we also have what are known as neutrino forms of these particles, so we also have electron, muon and tau neutrinos. All these neutrinos exist with almost no mass and they have a neutral charge, so they don't do much and effectively just exist to take part in particle interactions. And then of course we have the antimatter equivalents of each of these particles, which has the opposing charge to the regular particle. Okay, so now we know what particles are, we can now see the interactions they experience. We know from Einstein that you can't have instantaneous action at a distance, so there must be an interaction going on for a resulting action to occur. This is what led to the idea of 4 fundamental forces of nature, and then the idea of exchange particles, which are otherwise known as gauge bosons. These particles can cause 2 types of interaction between subatomic particles: repulsion interactions, where the particle exchange carries momentum, which causes the particles to move away from each other, and attraction interactions, where the exchange particle boomerangs around the particles, pushing them together. There are 4 fundamental forces which govern all forces in nature, and each has their own gauge boson which is used for particle interactions. Let's start with the strongest fundamental force, the strong nuclear force. This force uses pions as its gauge boson and only affects other hadron particles. The strong nuclear force is what holds together the nuclei of every atom in the universe, with pions being exchanged between the nucleons attracting them together. Following the strong nuclear force, we have the weak nuclear force, and this affects all types of particles, using W+ and W- particles as their gauge boson. An example of a weak nuclear force interaction would be the decay of a proton to a neutron. In this case, the neutron decay emits a W- boson, which then results in the production of a proton as well as an electron and an anti-electron neutrino. Now we get on to the two types of interaction you're most likely familiar with. The next strongest interaction is the electromagnetic force. This interaction uses virtual photons as its gauge boson and only impacts charged particles. These interactions can be seen between two particles with the same charge, such as electrons. When these particles have equal charge, they will repel each other as a virtual photon is exchanged between them. And finally, we have gravity. Gravity is the weakest of the fundamental forces, and has been theorized to use gravitons as its gauge boson. I say theorized because they haven't been confirmed yet, but we know that there must be some kind of particle for the interaction to occur. Gravity is a bit unusual, as it's weak to the point that particle physicists don't bother with it. Gravity only really matters when you have bigger masses like planets and stars. When going into any of these interactions, there are multiple things that need to be conserved going into and leaving the interaction. For example, let's take a look at an electron capture interaction. In this case, electrons and protons are attracted by electromagnetic interaction. But if the proton collides with the electron, then a W+ boson is released from the proton and taken up by the electron. This causes the electron to turn into an electron neutrino, and one of the proton's up quarks to turn into a down quark, which changes the proton into a neutron. So let's look at what's conserved in this interaction. We start out with a proton and an electron. This means that we have one baryon and one lepton, and we have one positive charge and one negative charge, meaning that we end up with no charge altogether. And out of this interaction we get no charge from the neutron and no charge from the electron neutrino, so that's conserved. And then the neutron is a baryon, so baryon number is conserved, and the electron neutrino is a lepton, so lepton number is conserved. So now we know what the fundamental building blocks of this world are, and how particles interact on the smallest level with particles and atoms. But how about something larger? Let's take a look at Minecraft's most valuable commodity, diamond, and one of Minecraft's most common commodities, coal. These two things couldn't be more different in appearance, but as you may or may not know, they are both made up of carbon atoms. Now, you may be wondering why coal and diamond look so different. Well, it's because they're two different allotropes of carbon. Allotropes are structurally different forms of the same element, and carbon is capable of making many different types of allotrope. Diamond is a giant covalent structure. This means that each carbon atom is joined to 4 other carbon atoms by the use of covalent bonds. These atoms form a regular tetrahedral structure, which is what gives diamond its incredible hardness. Coal, on the other hand, has carbon atoms arranged in 2D sheets. These sheets have each carbon atom bonded to 3 other carbon atoms to form hexagonal rings. It's interesting to note that there is an issue with Minecraft's diamond and coal. In Minecraft, you're able to craft using both diamond and coal, so that you can have both diamond and coal blocks. I'm sorry to say that this just isn't possible, at least with the size of Minecraft blocks. Diamond can't melt, so it's impossible to form a 1 meter squared block from it. Instead, when put under high pressure, diamond starts to burn rather than melt, producing carbon dioxide into the atmosphere. Even if we were to get rid of the atmospheric oxygen when exposing the diamond to higher temperatures, the diamond would just turn into another allotrope of carbon, graphite instead. So there we go, there's a bit of fundamental physics, and there's basically no difference between Minecraft's diamond and coal, or even lead from your pencil. So thanks for watching. If you enjoyed this video, then don't forget to like and subscribe. And please join me next time as I discuss if the Minecraft world can be a cube, how gravity works, and how strong the Minecraft world's gravitational field is compared to the Earth's. If you have any ideas for me to cover in future videos, then please put them in the comments down below, and I'll consider all of them. But until then, this has been the science of science with a little bit of Minecraft. I'll see you next time.